Hello dear classmates, welcome back to the fault modeling chapter. In the previous video, we have introduced the stuck-up fault model and the bridging fault model. In this video, we are going to introduce a third fault model, the delay fault, which was proposed in 1974. In this fault model classification tree, we will continue the gate level or intra-cell fault model. There are two popular delay fault models, the transition delay fault and the path delay fault. In advanced technologies, some defect behavior is not like stuck-up fault. The defect can change the circuit timing, but it may not change the functionality. For example, for a random defect, such as a resistive open, suppose we have a poor via or a poor contact between two inverters. If we apply a faulting transition at the input, the good output can be like this, but the faulty output is slower than the good output. It is not a stuck-up fault. The output is just slower, but it is not stuck-up. A second example can be a systematic defect, such as a crosstalk between these two wires. This might be a design mistake. These two wires are too close to each other, so they have crosstalk problem. Suppose we have a rising transition and a falling transition in the opposite direction. The output can be slower than expected. These two examples show that some defect cannot be modeled by stuck-up fault. So in 1974, Professor Brewer proposed the delay fault model. A delay fault caused a circuit fail to operate correctly at specified speed, but it produced correct output at slower speed. So delay fault models are important, especially for advanced technologies. So how to detect the delay fault? We consider two scenarios. For global delay fault, which affect a large area of the circuit. For example, wrong doping in our manufacturing process can cause VT shift, which is a global delay fault. To detect this delay fault, we can design on-chip process monitors, such as this 5-inverter oscillation ring. We can measure the output oscillation frequency to determine whether this chip has global delay fault. If the output frequency is lower than our expected value, then we may suspect that this chip has global delay fault problem. In the second category, local delay fault that affects only a small area of the circuit. For example, a poor contact or via can cause resistive open. In this case, we need delay testing to detect local delay faults. So what kind of pattern can we apply for delay test? As opposed to stuck-up fault, which need only one single test pattern, delay fault need a pair of two test patterns. In this figure, we can see that there are two patterns to detect a delay fault. Pattern V1 initialize the circuit state. For example, we apply 0, 0 to initialize this OR gate. And the second pattern V2 launch a transition and propagate the fault effect to the output to be observed. For example, we applied 0, 1 to this OR gate, which is our test pattern 2. We can control the timing T between V1 and V2 so that we can determine whether this circuit pass or fail the test. If the output rises before the time T, it passed the test. If the output rises after time T, then it failed the test. So, in summary, DelayFault requires a 2-pattern test. Now, let's move on to the details of 2 popular path DelayFault models, the path DelayFault model and the transition DelayFault model. The path DelayFault model, or PDF, was proposed by Smith in 1985. In the path DelayFault, it is assumed that the path delay of the faulty path is larger than the clock period. For example, given this circuit, suppose that we have a faulty path. Then the summation of the delay along this path is larger than the clock period. In this fault model, we assume that the delay is distributed along the faulty path. On the other hand, the transition DelayFault model, or TDF, assumes that the path delay of all paths through the faulty node is larger than the clock period. So, in the transition DelayFault model, we do not consider the path. Assume that this is the faulty node. No matter which path you propagate to the output, the fault can be detected. There are actually many different DelayFault models, such as the gate DelayFault model, which assumes that one single gate is slower than expected. For example, this one gate is particularly slower. Or a segment DelayFault model assumes that a segment is particularly slower. This different DelayFault model trade off the model complexity and the accuracy. A more accurate fault model is typically more complicated to handle. So let's give you a specific example about path DelayFault and the transition DelayFault. In this circuit, suppose that the clock period is 10 nanoseconds. For each gate delay, the good value is 2 nanoseconds. Now let's consider the path DelayFault model. The fault is distributed along the path. Suppose this gate delay is now 3.0, this is 2.6, this is 2.7, and that last one is 2.9. If we apply this test and we observe the output along the short path, because the accumulated delay is 8.3 nanoseconds, which is still smaller than 10 nanoseconds, so the circuit can pass the test. However, if we observe along the long path, the accumulated path delay is 11.2 nanoseconds, which is larger than 10. So the test result is fail. So we can see that for path DelayFault model, it assumes that the fault is distributed along the faulty path. And in the path DelayFault model, the fault size can be small. The fault size means the extra delay of each gate. On the other hand, the transition DelayFault assumes that the fault is lumped in a faulty node, and the fault size is pretty large. For example, this node is slower than expected, and the fault size is 9.0 nanoseconds. If we test the circuit along the short path, the delay is 15 nanoseconds, so it failed the test. If we test along the long path, it still failed the test. So for transition DelayFault model, it assumes that the fault is lumped in a particular faulty node, and the fault size is very large. So we do not need to consider the propagation path. We can say that path DelayFault is more accurate, but the model complexity is higher than transition DelayFault. So now let's see a particular example of a path DelayFault. For each path in the circuit, we have two potential path DelayFault, the falling polarity and the rising polarity. In this particular example, we have 5 paths in this circuit. They are AHK, BELHK, BEFJK, CELHK, and CEFJK. For each path, we have 2 path DelayFaults. So there are totally 10 path DelayFaults in this circuit. Now let's consider the path DelayFault BEFJK, which is marked in blue color. Suppose we want to test the falling transition path DelayFault starting from the input B. If we apply the pattern 00 for A, 00 for C, we can propagate this transition along this path, and eventually we can detect the fault at the output K. The gray area in this figure means that the faulty signal is later than a good signal. When we observe the output, we can detect the path DelayFault. Now, let's do a quiz. For this given circuit, how many path DelayFaults are there? Question number 2. If we apply a pair of test patterns 001 to 011, can we detect the BEFK rising path DelayFault? Now please pause the video and do the exercise. Have you done yet? In this circuit, we have 1, 2, 3, 4. Totally 4 paths times 2 polarity. So we have 8 path DelayFaults. When we apply pattern 0, 0 to 1, and 1, 1, this test pattern to detect the fault, we can have a falling transition here and a falling transition here. This is static 0, and the output would have a falling transition. So yes, we can detect the past delay fault using this pattern. Have you got it correctly? Now let's move on to the second DelayFault model, the transition DelayFault model. In a transition DelayFault model, each node has two transition delay fault. They are slow to rise STR and slow to fall STF. To detect a transition fault, we still need a pair of two patterns. Test pattern 1 initialize the pattern. If we want to detect a slow to rise fault, in pattern 1 we need to control the node to 0. On the contrary, if we want to detect a slow to fall transition delay fault, we need to control the node to logic 1. In pattern V2, we launch a transition and propagate the fault effect to the output. If we want to detect a slow to rise transition fault, we need to detect a stuck at 0 fault. On the contrary, if we want to detect a slow to fall transition delay fault, we need to detect the stuck at 1 fault. For example, given this circuit, suppose we want to detect B slow to fall transition delay fault. In pattern 1, we control B to 1. In pattern 2, we control B to 0. So we create a falling transition. And we need to detect a stuck at 1 in the second pattern. So C must be 0, and we propagate this effect. For the output of the OR gate, a good value should be 0 and the faulty value is 1. After the inverter, we have 1/0 for J, and we propagate this through an OR gate. Because the value of H in the second pattern is Z, so that we can sensitize this to the output K. For a good value, K is 1. For the faulty value, K is 0. In this way, we can detect a stuck at 1 fault in the second pattern. Since we already have a falling transition at the faulty node, and we detect the stuck at 1 fault in the second pattern, so this pattern detects B slow to fall transition fault. Now let's consider this circuit for a quiz. How many transition delay faults are there in this circuit? Question number 2. If we apply the test pattern pair 001 and 011, does it detect B slow to rise transition fault? Now, have you got it? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 different nodes by 2. So we have 18 transition delay fault in this circuit. Now, for question number 2, we apply 0 for input A and 0 to 1 to input B and 1, 1 for input C. Now, we want to detect B slow to rise fault. We can see that we have a rising transition from pattern 1 to pattern 2. And in the second pattern, we want to detect a stuck at 0 fault on B. After the inversion, the value is 0/1, which means the good value is 0 and faulty value is 1. After the AND gate, the output should be 0, 1 in the second pattern. And for G1, the output is 0 in the second pattern. And for output K, it should be 0, 1 in the second pattern. So if we see a 0 in the output K, it passed the test. If we see a 1, it failed the test. Since we already have a rising transition at input B and we detect the stuck at 0 fault in the second pattern, so yes, we detect B slow to rise fault. Have you got it correctly? So now we already have 3 different models: stuck at fault model, bridging fault model, and the DelayFault model. So are they really useful? Now let's see some experimental results performed by mentor graphic. This is a Venn diagram for a true experiment. The numbers in this circle show the portion of failing chip covered by each different test. In the middle, we see that a majority of chips, 57%, are detected by the 3 different tests. However, there are 0.5% of chips that fail only the stuck at test. There are 3% of chips that fail only the bridging fault test. And there are 20% of chips that fails only DelayFault testing. So we can see that from this Venn diagram, in reality, no one test can replace each other. In summary, in this chapter, we have shown that DelayFault is very important for advanced technologies, and we introduced 2 popular DelayFault models. The past DelayFault model, PDF, assumes there are 2 faults on each path: the rising and the falling polarity. The transition DelayFault model, TDF, on the other hand, assumes there are 2 faults for each node: slow to rise and slow to fall. This table compares past DelayFault and the transition DelayFault models in terms of the number of faults, because the number of paths in a circuit can be worst case exponential to the number of gates. So the number of path delay faults can be worst case exponential. This is very bad for large circuit because it cannot be scalable for large design. On the other hand, transition delay fault assumes that there are only 2 faults for each node, so the number of transition delay faults is linear to the number of gates, which is a very good news because we don't have to worry about the exponential number of faults. In terms of fault size and distribution, path delay fault assumes that the fault is distributed along the path, and it considers small fault size, which is very good and very practical for real circuit. On the other hand, transition delay fault assumes that the fault is lumped in a specific node, and the fault size is very large, so it does not consider the propagation path. This is not very realistic for a true circuit. In this table, we can clearly see the trade-off between model accuracy and the complexity between path delay fault and the transition delay fault. Path delay fault is accurate, but it's very complicated to handle. On the other hand, the transition delay fault model is not very accurate. However, it's very easy to handle because the number of faults is linear. Finally, before we end this video, please think about one question. We said that the number of paths is worst case exponential to the number of gates in the circuit. Please give me an example where the number of paths is exponential to the number of gates. So what kind of circuit can cause us problem? Please think about this interesting question. Thank you for watching.